Yeah, hi, I am Thomas and welcome to this presentation. So today I'm going to talk about our paper frequency response-based identification of nonlinear oscillators. And this is a paper joint work with Professor Balachandran at the University of Maryland, College Park. And this paper printed version is going to appear in 2025 in the Journal of Sound and Vibration. So to motivate the topic of system identification, we study generally mechanical systems and they interact to the environment, forces act on them. And due to those forces, we study those mechanical systems start to move. And one is interested in the movements of this or the motions of those mechanical systems. And one tries to understand and study and predict those motions. And then to this end, we need governing equations. And this motivates the topic of system identification. System identification, more specifically for nonlinear oscillators. I'm going to show you that on the next slide. So here we have a nonlinear oscillator setup, so a shaker experiment. So on the left-hand side, we have a shaker here, a sliding table, and which passes the excitation from the shaker onto this cantilever, which is the nonlinear oscillator. And I'm going to measure the strains of this cantilever with a strain gauge. Additionally, we see some tip magnets here which induce strong nonlinearities. And if we now supply harmonic excitation here, we can obtain such measurements, such frequency response curves, where we see a large region of bistability. And in the following, we want to utilize those measurements to automatically come up with a set of governing equations, such as those ones, which when simulated, accurately fit the obtained forced response curves. How do we do that? We achieve this by fitting the following models. So Q double dot are the acceleration terms, and these are some internal forces which could comprise linear stiffness, nonlinear stiffness, linear damping, nonlinear damping, and even more complex terms. And here on the right-hand side is the external forcing, which is periodic to start with. So the internal forces are now modeled by sum of library functions here, G. So the library functions are just library of functions, just a bunch of candidate functions, and I encourage you to throw in as much as possible to have a rich basis to approximate anything what might be going on. We're going to learn later on how to get rid of spurious functions. And so, for example, one basis one could use would be polynomials, which is very commonly used in nonlinear vibrations. But by all means, it could be also a very different a set of basis function depending on the application. And those basis functions are then scaled by some kind of unknown parameters, which we group in this vector capital N here. Furthermore, we are going to work in the Fourier domain. So the Fourier domain has a couple of advantages. One of them is in an experiment, I often only measure acceleration, velocity, or the position. However, to fit this model, I'll need all three signals, and in the Fourier domain, I can convert between them very easily. Similarly, the forcing will be expanded in the Fourier series, and then by equating coefficients, one ends up with a large linear system. And now stacking multiple measurements in the rows of this big matrix A here. So if you have enough measurements, we can end up with an overdetermined system. And then one can find a least squares fit, which gives me the coefficients here of these unknown library functions. So a straightforward least squares fit would do a poor job because remind yourself, I've encouraged you to throw as many library functions in there as you can think of. And including all of them would lead to an overfitted model, which poorly extrapolates, is most likely unstable, and contains a lot of spurious terms. So I'm going to show you now how we encourage the robustness of the fit. And first of all, we got rid of noise. So every measurement is invariably corrupted with noise. So from the measurements, we estimated the noise floor. And here we can see, for example, this is an exemplary measurements. We see that the excitation frequency has a large amplitude. We can also see clearly some other higher harmonics, but the majority of the amplitudes are below the noise floor. So in the large linear system, we truncate all entries which are below the noise floor to get rid of those coefficients. Secondly, we improve the conditioning of this large linear system. So it might happen that two columns of the matrix A are almost linearly dependent. So they point almost in the same direction. So we are going to delete one of them. So we have only one vector pointing in each direction. So this increases the conditioning of the linear system we are trying to solve. And last, we are simplifying the arising equation of motion. So after the first two steps, we still end up with usually we still end up with the overfit system. And we follow the strategy of only including those coefficients now which reduce the fitting residual significantly. So this turns out to be a forward stepwise selection procedure, and all these steps can be coded up, and we have coded them up in an automated software. So here this is a demonstration. So this is the shaker experiment. We obtain this kind of measurement, and then this is an exemplary output of our code. And so in the beginning, we delete redundant data. In the second term, we successively include coefficients to build a more and more sophisticated model. And after we reach some predefined tolerance, we end up with a final model. So this is the result here. And you can find the code here on GitHub. You can just follow this link. No, I'm going to show you that link later on. No worries, you don't have to click this link now. But you can download this code and play with your own experiments. So here is the model, again, in a little bit of a cleaner form. And we can now relate the rising terms to physical sources. So the first one is, for example, you can clearly see damping here. We can see stiffness term and the forcing term. And now if I simulate the equation, this equations of motion, I get a fit which accurately represents the measurement. So what else can I do with these equations of motion? So given you have now taken your mechanical system here, I've identified it, and most likely the environment you put the mechanical system in is not going to be the same as you tested in. So we're going to put our mechanical system now in different environments. And one way could be, for example, by varying the forcing amplitude. So now I still have it supply the forcing by the shaker here, but I supply different type of amplitudes, and I can run the experiment, and I can also run the computations, and I obtain the following curves here, where we still see a very good agreement between the measurements and the simulations. Only for very large amplitudes we see some deviation. So far we have only used the yellow curve here is only used for fitting. The rest are just pure extrapolation. So this is for harmonic forcing. We've also tested it for other common signals which are commonly used in structural dynamics. So for example, sine sweep, free decay measurements, or random excitation. And in all these cases, we see that our model accurately represents the experiments. So just as a reminder, we have only used this yellow curve, so only the data included in this yellow curve for fitting. The rest is just pure extrapolation. You might wonder if this also works for a higher dimensional system, and the short answer is yes, we can apply it. So to demonstrate that, we have studied a 3 degree of freedom structure here, so 3 cantilevers, and those springs here induce some coupling between those cantilevers. And when we do the force response curve, we see measure the force response curve, we see 3 peaks. So first 1, 2, 3. And now we fit a 3 degree of freedom system to it. We end up with the following set of equations, where again we can relate the terms. So there are conservative terms, damping terms, coupling terms, and forcing terms, which are well understood. So this is a very easy, accessible, and interpreted model we come up for this response curves. And if we now simulate the equations of motion here, we get a close fit with the measurements. Additionally, we have looked at internal resonances. So internal resonances serve as benchmark for many nonlinear vibration problems because they're inherently tricky to observe experimentally, to study analytically, and also numerically. Nevertheless, due to symmetries in structures, those internal resonances often arise. And they can feature very complex dynamics, such as, for example, here we see a response here of a 1-1 resonance structure where we have detached branches, which are detached from the main branch, so-called isolars. And if we supply this measurement now to the automated identification routine, we again end up with a very simple set of equations where we can relate the arising terms, conservative, damping, coupling, and forcing terms. And if I simulate these equations, we get back our measurements very closely. Additionally, we have looked at clamping nonlinearities, so the same setup. Only now the difference is prior to that, we had here a tip magnet, and also opposing on the other side, we had another magnet. So we tried this kind of configuration. The initial reason why I tried it was my belief that my attempt to study a linear system. So I thought, all right, we're just going to take off the magnets and then we're going to have a linear system. This is the outcome here, which is still does not feature, which does not represent a linear system by all means. We see the peak depends on the forcing level, which is only explainable by a nonlinear model. And if we run the frequency based identification on this kind of data, we come up with the following set of equations, which features also again conservative and damping terms and forcing terms. Last, we have also looked at an external data set. So far, I had complete control of what was going on in the lab, and I was running the experiments and the fitting myself. And now I was looking to external data where I could not, I had no control about the external data. I was just downloading it from the internet, from this publication. This is a jointed structure, and which is here with 3 bolted joints, and then it's excited by this shaker here on the right-hand side. And it's differently now that only the first harmonic is available for fitting, but even with this sparse data, we can come up with a model which represents the different forcing level quite accurately. By now, I've worked with various nonlinear structures. I just often just get external measurements and run the automated frequency identification. And we observe throughout the bench, we observe very good results, very good fits between the data and the models. The models are always very simple and accurately represent the measurements. So I'm happy to analyze any other systems. So you can either download the code yourself and give it a try, or just shoot me an email. I'm happy to work you through the individual steps of running a frequency-based identification for your nonlinear system. So just to summarize what we have done, I have presented a general system identification technique, and the outcome are sparse, simple equations of motion for nonlinear oscillatory systems. And I have shown application to single degree of freedom systems, where I have shown that those model or the obtained model extrapolates very well. Similarly, I have done multiple degree of freedom system and an internally resonant structure. Last but not least, we have also looked into joint and clamping nonlinearities. If you want to learn more, you're very welcome to look at our publication here. The code, as I said, is in GitHub. Feel free to download and play with it. And the data, the force response data, I've showed you in this presentation, and also which is included in this paper, is downloadable here by via Zenodo. So feel free to download it and have a look. So if you have further questions, you can also feel free to shoot me an email. Thank you very much for listening.